Good.
So first of all, let me apologize for last week. I made a mistake on one hand. Here, let me refresh your memory a little bit. It's easier if I draw it rather than try to explain it.
All right.
When you have three sides of a triangle.
Yes, sir.
A, B, and C. What you know is that A plus B has to be greater than C. And I think what I did is made it less than C. And that's why the answer we got on that log problem was wrong. Because I made it less than C. In other words, the way this works is that any side of a triangle is always less than the sum of the other two sides. And also always greater than the difference of the other two sides. And that's kind of the way I remember it, is it's always less than or the opposite.
Okay.
So it's less than the sum and greater than the difference. And so I think we had something like log base 2 of 4, or not 4, 3, plus log base 2 of 5. And it should have been was greater than log base 2 of x. And we end up getting the problem instead of less than. Okay? And I don't know, maybe I made mistakes on some other problems, but that's the only one I was for sure of after I started thinking about it.
Yes, sir.
That was a bit of a tricky problem. Anyway, what are we doing today? Are we doing calculus, or it sounds like your pre-calc course is fairly hard. If you got some problems in that to deal with, I'm happy to do that.
I think we're good going back to calculus.
Okay, cool. Where we left off was with related rates.
Okay, related rates.
Yeah. Let me grab my book. I'm torn between, since it's been a couple weeks, there's a couple of optimization problems that I wouldn't mind covering also. So if we had just finished related rates, I'd go do some related rate problems. But since it's been a couple of weeks since we've done any calculus, let's go back a little bit and let's talk about some other optimization problems.
All right.
And now the optimization problems are the ones that were like the corral. How do you build the corral to get a maximum area?
That's right.
Okay. And there's tons of optimization problems. One that is particularly interesting is this one.
Okay.
Okay. And the way to think of that equation is it's minus x squared plus. Yeah. In other words, minus x squared looks like this, right?
Yes, sir.
And plus 3 means it's a vertical shift up by 3 units.
Yes, sir.
So it comes out being 3 minus x squared.
Yes, sir.
Okay.
Just to simplify it.
Well, just you're going to end up with a lot of these problems where you have to translate it. In this particular case, they tell you that that function is 3 minus x squared. Okay?
Yes, sir.
The question is what's the maximum size rectangle that you can fit in there? Is it that one?
Okay.
Is it that one, or is it this one? Or is it something in between? In other words, it's not obvious what it's going to be. So when you are figuring an optimization problem, you have to first start with what is it that you're optimizing.
All right.
I'm optimizing that rectangle. And I want
optimizing the
area. That's what I want, is the maximum area. So where do I start on this problem?
A equals length times height.
Okay, good. Length times width, we'll call it.
Length times width.
What's the length here? Let's talk about area as a function of x. Because it is. It is a function of x.
All right. So do we want to set length to x?
Yes. That's exactly what length is. In other words, the distance from there to there, because we don't know what it is x. So that's the length. And the width being this measurement. What is that?
Okay.
In terms of x and y, what is that?
That is
y.
Okay. Just in terms of x and y, yeah.
Yeah, so our width is, excuse me, I got this wrong. The length is not x, the length is 2x. Sorry.
2x.
And I hate to make a mistake when I'm trying to explain an important principle, because it really confuses you, and I understand that. But yeah, in other words, if this distance is x, then the length of that rectangle is 2x, because you got the same x over there.
Yes, sir.
Would have helped if I'd have drawn the thing a little bit more symmetrical, but I think you can see how the length ends up being 2x.
Okay.
In other words, the length is from there to there. And this measurement is x.
Yes, sir.
And it's symmetrical, so it's two of those that make up the length of that rectangle.
Yes, sir.
Now, what's the width? In other words, what is y?
All right. So is that just is that y, or is that like
That is y. In other words, if I'm concerned about what that point is right there, it's 3 minus x squared.
Okay, so it's just y right now.
No, I haven't dimensioned this thing. I have no idea what these dimensions. Well, the only thing I know for sure is that that's at 3. But I don't have any other dimensions. In other words, if I'm looking for the height, or the width, rather, of this rectangle, it's y, because it's always on the red curve. So I can say it's y, but the key to all of these optimization problems is the fact that y is a function of x.
That's right.
So I can do this. What is y equal to? 3 minus x squared.
Ah.
So there's your area function. And it's a function of just one variable, x. So what's my next step?
Now you just have to, you would just multiply it out, right?
Okay, yeah, well, that's correct. My area function is 6x minus 2x cubed. Now what?
Okay. Now we would...
What do you always do? If I say you're in calculus, and what's the first step? What's the...
You find the root.
The derivative.
The first derivative. The derivative.
That's always what you do. If you don't know what to do and that's an option, do that. So what is the first derivative function?
Okay, so that's just 6 minus 6x squared.
Okay. Now, what's the next step?
Okay.
On optimization problems, this is always the next step.
It is.
Where does the maximum occur in the first derivative? I'm sorry, where does the maximum occur in the original function? 6x minus 2x cubed.
6x minus 2x cubed. The maximum occurs
When the slope is what? Of the tangent line to that function.
when it's when it is 0.
Yeah, exactly. So the next step is always to set the first derivative at 0. In other words, I don't have a graph of this original function. It's some cubic function. If I were to draw it over there, it probably looks something like that. Well, the maximum is right there. It's always the maximums and the minimums are where the first derivative is equal to 0. That's the beauty of differential calculus. That's the reason we pay attention to the slope of the tangent line, because that's where you find maximums and minimums.
Yes, sir.
Okay, so
All right.
we're going to set this equal to 0. So we got 0 equals 6 minus 6x squared. Solve that.
So it's 1 or
That's fine. Go ahead and do it that way. Now what?
Okay. I had first subtracted 6 to the other side, or could have added.
I just divided both sides by 6 to simplify it a little bit. Okay.
All right, so we have x squared is equal to 1, so x is equal to positive or negative 1.
Yeah, there you go. X is equal to plus or minus 1. So it's at 1. Why does that bother me? Because I don't remember that being the solution to this. Huh. Must be, though.
Does that mean that the length is going to be 2?
Correct. The length's going to be 2, and the height is going to be 2 also.
Okay.
So actually,
it's a square, so that would make sense, right?
No. Yeah, I guess. Okay, yeah, you're right. It's this one here. And it is a square. I just do not remember this problem coming out that way. But it does make sense, is that it's a square. I guess that's, I've been trying to teach you that, is that when you have an optimization problem and it's the closest thing to a circle that you can get, usually is the answer. But it's not the answer when you're building a corral onto the end of a property, because there's only 3 sides to that corral.
Yes, sir.
All right, but I don't know why my memory remembers the answer being root 3, but we'll go on. It's possible I've screwed up here on this. But let's take just a little bit harder one.
All right.
Yeah, well, what do we want to make that? Let's see, this is a lateral and a vertical shift. So it's going to be something like x minus 2 Make that 2 squared with a minus sign in front of it plus 3.
All right.
I think that's what it would look like.
We're trying to do the same thing now?
Well, no, the solution comes out quite a bit different, but that's why I say it's a notch harder now.
Okay.
Just because it's tougher to figure out. Question is, do I have the right function? I've just made this problem up. I'm not looking at anything, so I'm going to assume that that's correct, because that represents a right transformation, a right horizontal shift of 2 units. And that represents a vertical shift of 3 units, and that represents the fact that you're looking at a downward turning parabola.
Yes, sir.
In other words, it doesn't turn up, it's pointed down. And now the question is, what's the biggest rectangle you can fit there?
All right.
This is a bit tricky. In fact, I'm going to have to think about this for a little bit. Again,
So would we
optimization problem. So what's my first step?
Get the formula. So A equals length times width, and then set that in respects to x.
Okay. So this is a bit trickier.
So would we set it as 2x or just x?
What's that distance there?
That the pink line?
Yeah.
Is that 3? Did you mark 3?
3 is on the y-axis. I've marked 2 on the x-axis.
Okay.
In other words, the equation of that parabola has been shifted to the right by 2 units and up by 3 units. So those points are known. The question is, what is the length of that rectangle?
Yes, sir.
It's not x. X is the distance to the far side of that rectangle.
So could we do x minus 2 times 2 for the length?
I have to work this out again in my head. What's that point right there?
That would be, is that 7? Wait, no. That's,
well, what is that? That's where y equals 0. Okay, so solve this equation.
That's -3. Okay, so root 3 equals x minus 2. So root 3 plus 2. Let me set that on the calculator.
What's this point where it comes back and crosses the axis?
Okay.
This point right there? Where is y 0?
I think that's 3.372.
You know what? This function isn't right.
Or maybe I just didn't solve it right. I said y equals 0.
I didn't give it to you. In other words, when x equals 0, y is not equal to 0. So that point is not on the function that I've listed. So I've messed this up from the get-go. Let me not confuse you any further. let's just hypothetically call that 5, okay?
All right.
Now, boy, I just completely blanked on how to set this problem up. So my first suggestion is the best one. Let's erase it and go to something else.
All right.
It's a fairly complicated way of defining that rectangle. It's like 5 minus x is the length, and so forth and so on. Yeah, and I'm forgetting something about it. I'm not sure what. So, let's talk about related rates.
All right.
These are optimization. Just remember, optimization is you define the formula you're trying to maximize or minimize.
Take its
First
derivative.
derivative and set it equal to 0.
Yes.
And that's going to tell you everything. Now, sometimes the formula is difficult to set up, like that last attempted problem. But most of the time, you can figure out what the formula is. I was giving you an extra hard one, and I wasn't referring to a book. I thought I had it memorized properly. I didn't. So, let's talk about the cone. Wow, I knew how to draw a cone so well. Let's say you have a conical tank,
All right.
as shown in the figure. And the height is changing at a rate, height rate equals minus 0.2 foot per second, minute, excuse me. And the radius, rate of change, always remember that rate of change is derivative. That's what it means. Okay. The radius is decreasing by 0.1 foot per minute. It's decreasing, so it's a negative sign. The height is dropping, so it's negative.
Yes, sir. And is this like the height of a liquid inside of it?
Yeah, you got a liquid leaking out. Okay. For example, when water is drained out of this tank, the volume, the radius, and the height are all functions of time.
Yes, sir.
When all of the key variables are functions of time, or sometimes an angle, or sometimes something else, but time is the most common one. When you're doing a related rate problem, it's usually in terms of time. Okay? And what I'm attempting to show here is that the rate of the volume change is going to be a function of the rate of the height and the rate of the radius change.
Okay.
So it's the volume function that we're going to be dealing with. And let's say the question is, well, not yet. Let's just talk about related rates. What's the volume function?
All right.
What's the volume of that cone?
That's going to be the pi r squared h.
Okay, that would be the volume of a right cylinder.
Oh, wait a minute. 1/3 of that.
Exactly. It's pi over 3. Whenever you have one end of that prism go to a point, you lose 2/3 of the volume. So the final volume is 1/3 of what the volume of an equivalent cone would be. Just so you understand what I'm talking about, not a cone, an equivalent cylinder. So if you had a cylinder like that, it would just be pi r squared h. But the fact that it goes to a point means it's always 1/3 of that. And that's true whether it's a circular cone or whether it's a square pyramid. In other words, the same thing for a square pyramid is as long as it goes to a point, pyramid, then the volume is always 1/3. If you were sculpturing, if you started with a right cylinder and you were sculpturing a cone out of it, you know you're going to lose 2/3 of the volume by the time you're done. And that's a little unusual because you might think that it would only be half, but it's 2/3. So that's the volume of a cone.
Yes, sir.
Now, just a second. So here's the question. What is the rate of change of the volume when, and these always come with specifications about what radius and height are, when the radius is 1 and the height is 2. So when we're looking at that being 1, there's the radius, and that being 2. Okay. So we're asking for the volume rate of change. What's another way of defining that? In fact, what's another way of defining that? As opposed to writing it with words, which is what I've done, can we write it mathematically?
Delta H.
With respect to?
With respect to delta R.
Look at the units on that. Feet per minute. So what is it? It's respect to delta time. And that's the way all of these are going to look. The rate of change of the radius is also a differential. And incidentally, these differentials only come in pairs. You will never find an equation that only has one differential.
Yes, sir.
There's always two. They may be on opposite sides of the equation, but you always have at least differentials only come in pairs. There's no such thing as DH all by itself. When you're talking about a rate of change that is measured in feet per minute, or feet per second, or feet per hour, DH dt, or dr dt. So what are they asking for there?
All right, so that's dv over, is that just d time as well?
Yep.
Or?
All three of them are in terms of time.
All right.
And once again, most of these related rate problems are always like that. Okay? So now let's go back. Remember what our master formula is. It's the volume of that particular cone.
All right.
So what's my next step? I've got the volume equation, but I got all my things are DHs and DRs and DVs. With respect
all right,
to
so
what's my next step?
Do we just need to find the formulas for that?
Differentiate. Remember the standard answer of any differential calculus question. When somebody says, what's the first thing to do or the second thing to do? Take the derivative. That's just Always lock that in. If you don't know what to do, try that as an option. Okay. Well, I'm going to differentiate the left side of that with respect to dt, and I'm going to differentiate the right side of it with respect to dt. So what's the left side?
So that's just, wait, so what would we be doing here?
Well, when you implicitly differentiate a function, or an equation rather, and you're doing both sides of the equation,
yes,
the rules are the same. When you run into a variable that is not t, then you take the derivative of the outside of that variable and you follow it with a dv dt. If I run into r, I take the derivative of the outside and I follow it with a dr dt. When I run into h, I take the derivative of h and follow that with a dh dt. So whenever you run into a variable, not a constant, but a variable, that is not your denominator, you have to apply the chain rule and always follow it. So what's the left side become?
So that's going to be, if we're doing the inside and the outside, or
Go ahead. Take, what's the derivative of the outside? In other words, v is the outside.
That, okay, so would we just use, all right, let's see, that is
the derivative of 1. 2.
Is that
when I take
it's just 1. Okay, so we're not
1. When I take the derivative of v, it's 1.
Okay.
Followed by,
so we,
what do I have to follow it by?
So we don't, so we're not plugging in the
not
pi
yet.
over 3.
Not yet.
Okay.
First, we're taking the derivative of the left side and the derivative of the right side implicitly.
All right.
So here's what the derivative of the left side becomes. See why? In other words, the derivative of v is 1, but since v is not t, I've got to follow it with a dv dt.
Okay.
So that's exactly what the left side becomes. Now let's attack the right side. Start with that.
All right, so that's 2 pi over 3 times r.
Followed by a.
And that's just 1.
No.
But it would be dA.
Let's finish differentiating it implicitly.
dH.
dr dt. R is not t. So we've got to follow that thing with a dr dt.
Okay. Okay.
What's the derivative of h?
1.
Followed by.
But since h is not t, it's dH dt.
There you go. And now you're getting hand. 1 second. Let me close my office door. Now you can kind of see what's going to happen here. They're saying, I need room to write. I'm going to erase this up here just so I can continue this thing. So I got this equation at the bottom, and it's an equation. Now I plug in. Well, the question is what is dv dt? So this is what I'm solving for, is dv dt, and I already have it all the way on the left side of my equation. Well, that's 2 pi over 3, and they say when the radius is 1. So I'm going to plug in 1 for r.
All right.
By dr dt. times dHdt. Now, they have given me that, and they have given me that. So now I have an equation that only has one unidentified thing, which is what we're trying to solve for. What's dr dt?
That is minus 0.1. I see. I see.
And what is dH dt?
That is minus 0.2.
Did something wrong.
Oh.
Trying to figure out what. And the reason I say I did something wrong is that we're coming up with a positive dv dt. Right?
Right.
In other words, this whole thing is a number. And it's a positive number. So this one is telling me that my volume is increasing as the radius and the rate are decreasing. And clearly, it's going to come out to be positive, which means it's growing. The volume is growing with time, which is impossible. So, gosh. These cone problems tend to be the hardest ones.
Was I meant to plug them in right then? Was that the proper place?
Yeah. Once we have this equation down here, then you plug in the R and the H. We don't have an H anymore, and I think that may be where my problem is. Yeah. Because H is actually a function of R.
Okay.
However, yeah, I tackled a problem that is harder than I immediately know how to do. Jesus, I apologize, Garrison. I don't know what's wrong with me today. Well, let's just go on again. Yeah, we're not done with related rate problems and optimization problems. I will figure out where I went wrong on all of these and get back to you. But I do believe you kind of got the hang of what we do on these things. By differentiating the entire formula, you end up with a dv dt, a dr dt, and a dh dt, and they've given you dh dt and dr dt. And then they're asking, what does dv dt do when r is a number and h is a number? And yeah, I've made a mistake on this, and I'm going to have to go back and review it. I don't want to do that on your time. So again, let's go forward and talk. The next thing in my book after related rates is extrema. And we've already talked about extrema a little bit. Yeah, let's talk about more based on this curve right here. And that function is f of x equals x squared plus 1. In other words, it's y equal x squared shifted up by 1 unit.
All right.
Now, if this function is also only defined from these 2 points, the end points, doesn't go beyond that. When you see a closed dot like that, it means the function stops there.
Okay. Yes,
So
sir.
the domain is restricted between there and there.
Yes, sir.
Okay. Now, if you're asking where the minimum occurs on that function, we know that the minimum is either, and this is important, it's either where the first derivative is 0. Remember, the first derivative is where that is flat. And clearly that occurs at that point 0, 1. So I know the minimum occurs where my slope of the tangent line is 0. So right here, if I took the derivative of the function, I get 2x. I said 2x equal to 0. Well, that occurs when x is 0. Right?
Yes, sir.
However, I don't actually know that I've found a minimum. It could be a maximum. Because all I know is that at the minimum and maximum between the 2 endpoints, the slope of the tangent line is always 0. And you have to investigate further to really actually mathematically determine that that is the minimum and not a maximum. And we've talked about that a little bit. In other words, if I have this function down here, well, there's 2 places where the slope of the tangent line is 0. So just taking the derivative and figuring out where the slope of the tangent line is 0 tells you you have a relative minimum or maximum, but it doesn't tell you which.
Okay.
Okay? We'll get to that in a second. But just know that no matter what your function looks like, all of these local minimums, there's a local maximum, there's a local minimum. Every one of them has the slope of the tangent line equals 0. So one way to identify local minimums and maximums is to take the derivative and set it equal to 0.
All right.
Okay?
And you would just use the graph to determine whether it's a local minimum or
there's
maximum?
a mathematical way to determine whether it's a minimum or a maximum, and that is to take the second derivative. So when you take the second derivative, if it is greater than 0, is concave up, making it a minimum. If the second derivative is less than 0, it is concave down. And that's pretty easy to remember because concavity up goes with greater than 0. Concavity down goes with less than 0. The tricky part is that concavity up means a minimum, whereas concavity down means a maximum.
So it's just
why?
like which way
because concavity up is like that. That's a minimum. Concavity down is like that. That's a maximum.
So it's like telling which way it opens.
Yes. In other words, on the function that I've drawn in the upper left, that we took the derivative and solved it. It's at x equals 0, but we don't know if it's a minimum or a maximum until I take the second derivative. And the second derivative is 2, which is greater than 0. So since it's greater than 0, it has to be concave up, and that means it's a minimum.
Yes, sir.
This thing called concavity is extremely important in differential calculus. Whether something is concave up or concave down, frequently you can see graphically that that means if it's concave down, it's a local maximum. If it's concave up, it's a local minimum. You can see that, right?
Yes, sir.
And mathematically, you figure it out by taking the second derivative. Now, sometimes the second derivative is equal to 0. Then it becomes a little trickier. So there's a second test. Whenever the second derivative is exactly equal to 0, you have to do a different type test. But I don't want to complicate things that much yet here. What I'm mainly trying to talk about is local maximums, local minimums, and absolute maximums and absolute minimums.
Okay.
Okay. So let me erase this over here. Let's go back and look at this first function that I've drawn. Well, if we look at that graph, we can tell that that bottom, at this point right here, is the local minimum, and it's also an absolute minimum, right?
That's right.
Okay. Where's the absolute maximum?
That would be
here. Let me
on the point on.
Let me put that point on there. Let's see. That obviously this is it, right?
That's right.
That point is when x is 2, which is the right end of the domain. In other words, x has to go from -1, I think, to 2. Or certainly to 2. That point right there is 2.
Yes, sir.
And that is not a local, but the absolute maximum. In other words, the difference between absolute and local is always in a very narrow domain, but absolute is over the entire domain of the function. And we can see that that's the highest that y ever gets. Or actually, I should label this f of x.
Yes, sir.
And the absolute minimum is also at 0, 1. So we now know where the absolute minimum and the absolute maximum is. If
That's right.
I change this, and this is going to be a little tricky to get, to understand. So that it's open on the ends.
Okay.
Where's the absolute maximum now?
Is that going to be a limit?
No, actually it isn't. That's why this is a little tricky to get. Because you can look at this as, well, that looks pretty high, right?
That's right.
There's a further point I can go. I can go closer to that line, to that point. That might be the absolute maximum. Now I can go further closer to it. There is no, there is no absolute maximum. Sorry, I'm having to write with my cursor because my thing went out. You still there? All right. I'm here. You there? Okay, let's finish the audio on the phone. Let me plug it in. Give me a second here. First one, did you get kicked off, or are you back on? Okay. Okay, here, let me plug my phone in so I can talk. Okay, so the question is, or did you get kicked out of the meeting? It says you're offline, so I don't think you can tell what number I just am writing. Wow. The thing is, my pad went out at the same time you got kicked off. So I'm tending to think that it might be on my end. My drawing pad went blank. That can't be from your end. So hold on a second here. Stay on the phone with me here. I'm going to close go to meeting out. I'm going to reopen. Yeah.